All right, guys, I'm going to start the recording here. All right, so today, I've basically given you at this point all the code, right? So, and really what's left is theory. So we're going to, as I said, we're going to go deep into all the different little things, what they are, what they mean. So today is more of a formal, that's why I needed the pen today. It's more of a formal description of neural networks, basically. Here. Let me try this one. I do not think it's good. Oh, we'll just use the slides as I have them. All right, so really all the materials are on Brightspace, so that's really what I'm going to use then. So let's navigate 365, contents. All right, so basically here this is the module that we're doing today. So these are all my notes, the description of neural networks, some of the background and theory, okay? And so that's what I'm going to start discussing. So we're going to start with linear regression, and just tie it to neural networks, and then we're going to build from there and add all the constructs that we have available. So let's take a look at these. You can see here, I did add some additional links. So actually, I'm going to show you this. If a lot of what I'll be saying is in these two blog posts, right? So NN's background, so you can take a look at that. So basically all of this is what I'll be describing in detail. We're going to talk about performance, getting started with deep learning. So some motivation about linearly separable data. And then this, some definitions, basically. Some of this we've covered already, of course, but you can read through this. So linear regression, some of the intuition, some of the equations, what is linear regression, and how it translates to a neural network, basically, okay? So this is, some of the concepts that I'll be talking about. All right, so you can read through this one. Linear regression leads into logistic regression. So we're also going to talk about that. So you can take a look at that. These notes, regression versus classification. And then these are some of the equations now for linear regression and logistic regression. Some of the intuition, activation functions. This is actually softmax, which we will do an example of today. And then this is the neural network for logistic regression. This is the binary cross entropy, a lot of fun, right? So as I said, this is all the things that I'll discuss a little bit more. Usually I like to use the whiteboard, so hopefully by Thursday, I'll have the whiteboard again. If I find my pen, so I'll describe this, but you can read through these notes here, which is the same material. I'll talk about this in a lot of detail. This will take a while. It's one of the most difficult concepts possibly to understand. And it has to do with the loss functions. Okay, so, but you can read through all of this. And then there's some examples. I use another data set called a wine quality data set that I like to use. So you can take a look at that. multi-layer perceptron, and deep neural networks, right? So same thing we've done, histograms and before. So I'm really just showing you a resource that you can just read from beginning to end, and it has everything in it. Okay, yeah, so. All right, so you can read through that. This is basically chapter 4 of my book, and it's just basically getting started with deep learning. All right, so that link is provided, and you can read through it. Another material I provided, just going up. Yeah. And then another material I provided, if we go to this same, remember, I'm in table of contents. And we've covered all of this. This is the last thing we covered last week, and I'm in this one, linear to logistic regression. Okay, so a lot of this is getting into the theory, the background, everything, all the elements. But this is a key module here for you to look at. So I clicked on this one, NN backgrounds. You should also take a look at this one, optimization. And so this has, KNN, which you have already looked at. It's got some of the metrics, object-oriented. We've talked about that. It's got the precision, recall, all that information. So you've covered that already. But it's got this concept of optimization, which is definitely one that we will be covering in the next couple of weeks, right? So this is one of the critical things, all right? So theory, and so this graph in particular, you'll see me referencing a graph like this one quite a bit. Okay, and then some additional ideas of calculation of the gradients, and so that was KNN. So you can take a look at this one as well, okay, as a reading material. All right, so those are some of the reading materials that I provided. So there's a lot to read for sure, as this is all the background of neural nets. And then after that, I have these 3 PDFs, basically. So I have linear regression, this one. Okay, so this is something that we're going to cover today. Okay, so there's those notes. And there is logistic regression. All right, and these are basically also the notes that I was going to cover today. Okay, some of the activations, etc. So I'll kind of have to pick some of these concepts that are easy to address without the pen. And then on Thursday, I'll get back to it. And then the last one should be this one, and then MLPs and DL. Okay, so this is the contrast of the different neural networks that are available. So we'll talk about this. Okay, so this is basically very critical background and understanding of how things work. Now, these are not things you have to code per se, right? But it's really about understanding what PyTorch is doing under the hood. You see what I'm saying? So that's really what these topics are about, okay? So we're going to start, I guess, with a simple neural network, which is the y equal wx plus b, right? And that really goes back to the line equation, okay? And we're going to tie that to linear regression, okay? So that's where we're going to begin. But anyway, I'm just pointing out that these are all the materials I strongly recommend that you read all of this, okay? The final exam will be based mostly on this, okay? So because this is the foundation of neural networks. So please ask questions if you have. All right, so I'm going to start with this one, linear regression. And I guess I'm going to start with this slide here. Okay. All right, so basically, we are building a neural net, right? So In a neural net, we've seen that the standard equation for this is y equal wx plus b, right? So you remember, from high school pretty much that you had a line equation called w equal mx plus b, right? Which gave you the slope, which indicates, the slope of this line, and then the b-intercept, which basically tells you if it starts at the origin or a little bit higher up, right? So what's important here, though, is that this equation, we need to learn the parameters m and b, right, for the equation. And once we have them, effectively, we have a way that whenever we give it an input, it always puts the value somewhere on this red line. Do you guys see that? So that's the basic essence of this. If you notice, so the concept of bias, which we always have in machine learning and PyTorch, right? So we have the weights and the biases is basically, you can see it right here. It's this little b. So without a bias, it starts at the origin, and with the bias, it goes up a little. It's a modification of the function, basically. But it's one of the parameters that we learned, okay? And then we have the set of weights. Now, this one only has one weight, right? For this very, very simple example. But as you guys are aware, in deep learning, you have many, many, many weights, basically. All right, so the idea then is that we want to build an equation that represents the red line given the data of the dot, the blue points, basically, right? So this is usually referred to as fitting a line through the data. But that's the objective of linear regression, okay? Now, that machinery, though, is actually the same machinery that we do for building neural networks. This is a very similar concept. We are building, you can think of it as we're building these lines, and then we want to create new constructs that allow us to create something more powerful than lines, right? So that we want to go from linear models to nonlinear models. So a linear model just means whenever you have equations that build straight lines like these red lines. Do you see that? If we were talking about a curve or something like that, then it's no longer linear. But for that, we need a different set of equations. Do you guys understand? So that's the basic underlying concept. Okay, so you guys have done linear regression. So when you did, you've done regression, basically. Regression models are sort of like this. You give it x2 and you want to predict y2, basically. Right? And we do this with this equation here. So now the question that we're going to do is we have to think about two things. We're trying to learn models. So that means we're trying to learn these things. Given inputs, x's, and parameters, m or w and b, we are trying to predict values here in the y. Now, these can be regression values or they can be classification values, like the labels. It's the same mechanism. That's actually, so let me give you this insight, for instance. When I learned about this stuff many years ago, there was linear regression. In my understanding, in my head, there was linear regression, and then there was neural networks, two separate things. And I didn't actually understand that they come from the same thing. And that was critical for me to understand. Instead of all these separate things, they're actually just like evolution. You start with linear regression or you start with a perceptron and you start building up until you arrive at deep learning, or even the last thing that you kind of learned about, which was called the CNN. That's where your learning will stop with regards to deep learning in this course, right? If you continue to other courses, etc., you'd get to see other algorithms that are even more advanced, more complicated too, and also more powerful. But they're all related, all right? And this is one key concept that you should understand, that the starting point is this. Now, so basically, we are trying to learn a function called the inference function that, given values, predicts something. Now, it could be this line like this, or it could be a line like that, right? So it could be in any shape. So it's almost like we can rotate that line, right? Depending on the goal that we have. But to learn these parameters and these equations, we need a methodology, right? So think of it as we're going to have a second equation, all right? So in machine learning, there's going to be these two equations playing, if you will, against each other or with each other, or however you want to see it. But one is called the loss function and one is called the inference function. Okay, guys? So that's really important. And also, just like there are two equations, there's going to be two graphs like these, or two charts. Okay? So one that captures the inference behavior and one that captures the loss behavior. And that is like the critical concept that I want you guys to grasp, okay? There's two equations, one for inference, one for loss. They work together with the goal of learning these parameters here, the B's and the M's or W's, right? Based on some objective. Usually we have some data that we want to learn from, right? Like we have images of handwritten digits or the cipher 10 and the labels themselves, all right? So what you need to learn is how does having, inputs and outputs in the training set help the model to learn this equation, right? That captures and learns how to predict given inputs. Does that make sense, guys? That's the key concept. So here's an example of what I'm talking about. This is for linear regression, for instance. The objective is what? For linear. Now, remember, there's regression. And regression could be linear and nonlinear. Okay? So again, linear just means you're fitting a straight line. It is just a straight line, always. Infinite from, one in one direction and the other, but always a straight line. There's only so much, as it has been found, that you can do with linear approaches, okay? There's only so much. Neural networks can create nonlinear functions, okay? But that's a different thing. So I can have, for instance, a regression that's curvy here, and I could have a classification that's curvy. And that would create, if you want to think of it as a nonlinear model, okay? If I have this blue line straight and this green line straight, then that means I have also linear models. So these are the models, okay? You can almost think about all this work just to create that green line in a sense, okay? So that's kind of what the model is in a very simplistic way, okay? So here in the regression example, we only have red dots because they're all pretty much the same group. And then what we want to learn is we want to learn the best line that fits the data, okay? That's this purple line. In a classification problem, we have a different thing. We're still trying to learn a line. If you look at this purple line and this green line, how are they different, really? Yeah, go ahead.
One on the right, pretty much identifying the difference between top part and bottom part.
Exactly.
The other one is like the ones that are in common form a line.
Yeah, exactly. And also, but in essence, the line is the same, right? So this purple line is no different than this green line. What changes is really how you position it in relation to the data, which is your answer that you just gave. So in this case, and what that means is, and this is really important, machine learning models are trained based on an objective. Okay, they have a goal or an objective. You want ChatGPT to solve high school math problems. It's a very complicated objective, but it's still an objective. Or you want this robot to pick up some boxes and take them over there. That's an objective, right? So in this case, this is a more general objective of fitting a line through the data versus a line that separates two groups of data with the least amount of error. Do you see that, guys? Does that make sense? So you can see why I wrote here linear regression for this one, and this is classification. So here we have the idea of red dots and blue dots, and we are trying to learn a green line that best separates the data. This is where I wish I had my whiteboard, because usually what I do is I draw a line here, draw a line there, draw a line there, and obviously those are not great lines. I guess I could do this, right? So I could fit other lines. like, that's a line, but it's a bad line. Now I can fit this line. It's kinda as good as the other one, but there's some error here. You see those red dots that fall on the other side? This seems to be the best one, but it could be this one, or that one, or that one, you know. You can, an infinite amount of lines. You guys understand? So that's kind of the objective that we are trying to do in a very simplistic way. And this is real. This is not an analogy or something like that. It's a very real thing that is happening when the model is this simple. Okay? So we're trying to, so what do we need? Here we need y equal wx plus b, right? And here we need y equal wx plus b. However, the w's are being adjusted. That's what you need to understand, right? You change that w and that thing moves, right? And so hopefully you capture the idea that the w's get to the optimal point when you have what? When all the red dots are on one side and all the blue dots are on the other side. Do you guys see that? And how do you do that? Well, the way that you do that actually is, you've seen it in the code. You start with a model, some green model, and the model gets inputs, predicts. And what happens? If it's a bad line, it's going to be somewhere here. So it's going to have this number of errors. You see, it's going to say, okay, I'm on this side. I marked these as blue, but they were actually red. So this is the number of errors that I had. In another iteration, the line is going to be more close to here. So now you still have a few reds on the other side, but not as many. So what do you say about that? The error is lower. You see what I'm saying? You have a lower error. And when the line is this green one, what do you have? In this example, all the reds are on the red side, all the blue are on the blue side. So what's your error here? 0, right? In this exaggerated example. And how do you get those values? You get it because you have training data. You give inputs to the model, and the model says, it's red, I predict red. You look at the real value, that's where we did that comparison. Predicted red, it's red. Okay, perfect. And then it's blue over here, and I predicted blue. Perfect. Nothing was an error, so then you minimize that. And that's what is done when we were doing that loss function. Remember when in the code we have something called a loss, and we have the training, and the loss is going down. So what's happening there intuitively? As the losses start, probably you have this, right? When the losses start. And then as it starts going down, what do you think is happening to the line? Until eventually you get, you see that in this very simple example. Obviously, a neural net is not going to have exactly this shape, but that's the intuition, which is a really important concept to understand, that the weights control the shape of the line, and the line then is used to predict where the values fall, and the predictions are compared to the real values to minimize that error, basically. Got it? Does that make sense? All right, so this is a very true concept, and we're just going to drill. It's just that one idea, and we need to drill down into all the different aspects of it, okay? So I have this one over here, which I really like, this graph. I think it's a good one. Let's take a look at it. Again, we're not going to be training linear regression per se, although you can with PyTorch. You totally can. But it still helps us to grasp the concept, because if we try to understand what a deep neural net is doing, it's a lot more complex. But in essence, it's the same thing. So what do you see here? I have a set of data, right? These blue points. Do you see those blue points? Okay. This is what? Is it a classification or a regression problem? It's a regression problem, right? What am I trying to do? I'm trying to fit lines through the blue dots. Do you see that? Yes? Okay. I'm labeling one red line A and the other red line B. So this is usually a loss function. Okay, Henry kept asking what a loss function was. This is your first loss function, MSE, or sometimes called LSE, mean squared error, right? Or least squared errors. But what is it? We're going to look at it with equations and everything. we're totally gonna go into equation mode, but I want you to think about this picture. Yeah, Henry.
The mean squared loss would be, you just do a summation on all the test set and whatnot.
The predicted versus the real squared.
Yeah, and then you would just.
The sum of the
and
errors.
You take the sum of that, right? And then multiply.
That's what I'm doing right there. That's exactly what's going on. So, but I want you to see intuitively why it works, right? So I have here just two models out of an infinite number of models. What are they? A and B. Do you guys see that? Intuitively, just by you guys are humans, you're intelligent, but a computer doesn't have everything you have, right? So it has to use other methods. So just based on what you see, which model is better? A or B? B, why? The line is going through the dots, right? Or stated more in terms of machine learning, the sum of the errors of line B is lower than the sum of the errors of line A. Do you see that? And that's, believe it or not, all that's happening in the background. You're going to take all the differences, square them, sum them, and you look at that value. And then for the other model, you're going to take all the differences, square them, sum them, and you're going to have a value and compare the two. The one that has the smallest difference is the best one. So how can we see that? You can see here written out. You can see that there, a little bit bigger. So notice that you have the data, right? The data here. And you need to compare. So you gotta think of it like this. I'm looking at point x2. So you guys agree that there's point x2 and point x1 here, right? So you see those 2 points. So at point x2, you want to predict the value on this axis, for instance. Do you guys see that? That's what you're trying to do. So the real value of x2 is this dot, the green one, right? Why? Because it would be one of these blue points. There are no blue points out here. Do you guys see that? So it's basically so at x2, the real value is this point here, the green one. For model B, it is what? This blue point right on the line of B, because that's what B is. B is a function, right? There is no line. There's no such thing as a line, really. What you have is a function. When you give it an input, it gives you an output. And then when you plot all those points, you get something that looks like this straight line, but there is no actual line, right? Just like in the previous example, you know, there is no red line here going through the blue points. What do you have? You have this function that, given an x in this axis, gives you a y on this axis, but it just so happens that when you plot it, it's always that red line. Do you all agree with that? Any questions on that concept? So there's never lines, no such thing as lines. However, there's functions. And these functions can approximate almost anything, with neural networks in particular. So now we go back over here. So I look at x2, right? And for x2, the real value is this green dot. If I plug x2 into my model B, which is a function, I get this blue dot over here, right? So now what do? I take the difference between them. So that means this little straight line between the green and the blue. That's the difference, just for that point. Okay? Then I repeat the exercise again for x1. I think that's what that is. So x1, the real value of x1 is probably this blue one. Yeah, this blue one. Do you see that? So at x1, the real value, so, you know, so the other value would be here. So they meet and they create that. That's the real value. Yeah? Now, if I plug x1, this one, into the function b, what do I get? I get the blue point on the red line, exactly. Got it? And what do? You take the difference between this point and the real point, and that's this. So it's the straight line between them. Got it? So now think of that as x1 x2. Okay, so then for model B, that's D1, D2, the differences. I'm going to take those two differences and I put them in here, plus all the other differences for all the n points. Got it? All right. Now let's take a look at the second model, model A. How do you create this model? It's a y equal wx plus b, right? Same x, but these w's and these b's, the weights and the biases, which are called the parameters, are what? Another set of parameters. Another set of weights that you have in this model. So whenever you plug in values into that function, you get this red line over here. Okay, so now let's take a look. Whenever I plug in x2 into this red line, I get this green dot. Do you guys agree? Everyone with me? And then when I give it x1 here, right, and I plug it into this model A, I get this green dot on the red line. Do you see that? Okay, so what do you do now? You need to calculate the difference between those points and the real points. What were the real points for x2 and x1? This green dot here, and then this blue dot here. So now you take the difference. So it's going to be the difference between here and here. That's the straight line. That's going to be called difference 2. And then the difference between this point and that point, another straight line. And let's call that one D1. Got it? All right. So now, if we look over here, the MSE is quite simply just looking at the sum of the differences. I didn't square them, which I should have, but for simplicity, I left it unsquared. But if you look, we just take all the, I only did 2 differences, but really it needs to be for every single point in the data set, the train set, the batch, whatever it is, whatever you're looking at that moment, all those, maybe a batch of 64 points, right? So you take these n differences, and that's these over here. So think of them as the n differences. You would square them, and then you take the sum of them. And then for model B, which is the one that's closest, you take all the differences, you would square them individually, and then you would sum them. And then those two are compared to determine which model is the best. Do you guys see that? So in this case, obviously, just intuitively, you know that these look bigger, right? D2 and D1 for model A. So they should, in fact, be bigger and much bigger than when you sum these for model B. And that's it. Yeah.
Bigger in difference, though.
Yeah, in difference. Yeah. So that I'm talking about these D's here, and really the sum of them. So for instance, the difference between this and this might be like 4. The difference between and this might be like 4.5. But as you can see, the difference between this little green point and this one is probably like 0.2, and this one 0.5 maybe. 0.2 and 0.5 gives you around 0.4. So that's the average, 0.4, versus this one is 0.25. So 4.25 is bigger than 0.4. You see that? But in essence, that's MSE. Does that make sense, guys? So this is the feed-forward section of the neural network or a linear model where you basically arrive at this at the end. So you give it inputs in a batch, you get to the end. When you get to the end, you start comparing the real versus the predicted. And then you use that information to update the weights. So we don't, because here in this example, I haven't told you how the weights are updated, right? All I'm saying is you have model A and model B. And I'm saying model A comes from some set of weights and model B comes from some set of weights. Obviously, these are better, and that is captured here. But how do we use this information to update the weights intelligently? Because we cannot update the weights randomly. That would not work. We would never have, it would take the life of the universe before we could randomly find the weights, if that makes sense. So we need to have an intelligent way of finding the weights. But this captures one of the functions called the MSE, or the loss function, mean squared error, okay? And then we need to understand then how that information is used to get the rest. All right, and that's where the contributions of Jeffrey Hinton, several algorithms come in that help us to do that, right? Stochastic gradient descent in particular, which is one of the concepts that we will learn about, okay? But currently, we're starting here. Any questions on this? All right, so we talked about that. Okay, so I said that there's two functions, right? I said that there's two functions. Which are this one, y equal wx plus b, which has a representation like this one for linear regression, for instance. So, but there are, in fact, remember, two equations, the inference and the loss function. The loss function is the function that governs this behavior here. Okay, so how does that compute it? So you'll see it always written, you can see it, I kind of wrote it down here on the upper right-hand corner. I have equation 1 and equation 2, okay? So now I've generalized the inference equation to be y hat equal wx plus b, okay? Now keep in mind, for simplicity, that's still just for one variable, unless you make the assumption that this is a vector, which you can't. For MSE, linear regression, this is what you will generally see as the equation for it. So I'm sure wherever you go, you will see this a lot, right? So this is y minus y hat squared and the sum of it divided by n. Does that look familiar? That's the same thing as this, right? You see that? Why? Because this is a sum. This symbol means sum in math. Well, I have d1, d2, d3, dn. I just sum them. You see that? That's it. Sum them. Why do I divide it by n? Because it's like an average of whatever, however many n's I have. Although really, if you look, if you're consistent, that probably is not necessary, right? But you can see that there. And then what do you have here? You have this y minus y hat. So what is that y minus y hat? Who can tell me? What is that y minus y hat? In this graph over here, this one. Yeah. Okay, so you know this from some class that you took, right? The residuals. But just in the graph, what are y minus y hat? What is y and what is y hat here in this picture? Exactly. So for example, x1, what is the y real? This blue point, right? That's the y real. And what is the y hat for b? It's this one, right? Do you see that? So it's basically the difference of the two. Does that make sense? So, you know, that's the connection, really. I mean, if you look at these equations, it's, you know, it's just the same as this graphical representation, okay? But notice that this is the example of the inference function, and this is the loss function, okay? So the loss function, I said, it's a second equation, right? It's a second equation. But the nice thing about it is, if you look at y minus y hat, which is the predicted, is really just the other equation, the inference equation. So you can put them together in this notation here, right? Because now you have y, which is this same y, the real, minus, but now instead of y hat, you have in parentheses y. What is y hat equal to? wx plus b, wx plus b. Do you guys see that? And so really, you're just taking the inference function and plugging it into the loss function for you to do the optimization. And that's it. This is literally the objective that you're trying to achieve. So when you're doing this kind of computation, you're comparing the real to the predicted. The predicted comes from this equation. We are trying to learn these weights and biases during the training that produce y's that get compared. And then this, basically this square here, we denote as j. And that is the thing that we are trying to minimize, that loss, as it's called, the loss function. And that's it. That's kind of the concept that you have there. Any questions so far? Making sense? Pretty important. All right, so just like, and I'm sticking just for linear regression, just like linear regression is represented by wx plus b, right? And it gives you this graph. This j over here, which you can denote as this one, equation 1, or this version of it written up here, has another graphical representation. And its graphical representation looks like this. This graph over here, okay? It's a different one. So there's two, okay? So I'll repeat this a lot, okay? But there's two. So it's different, right? This is a different equation. The previous one is just a line separating the data. This one, what is it? It's like a bowl shape or a little curve. You see that? Like this? That is called a quadratic function, okay? Basically, just has this shape like that. But that actually has a lot of important properties. Now, one thing that does not live in this graph is the data. The data lives here in this other graph. Okay? So it lives in that other graph, but this one just captures what? The difference between the real and the predicted. Okay? So you have to understand this part here, which is really important. So this whole thing in the square could just be x squared. And then it becomes something familiar to you from high school. What was x squared? X squared, right? Is a function. And it produces a graph that is bowl-shaped called a quadratic function. I can give you a simple example right now. 0 squared, 0. 1 squared, 1. Minus 1 squared, 1. 2 squared, 4, right? Or yeah, 2 squared. Minus 2 squared, 4. You see how that goes? So it's going like this, always has this behavior. And that's why you always see when people are talking about the loss function, this shape like this one, a quadratic shape. And everybody loves a quadratic shape, and I'll tell you why. But does this part make sense, guys? So I want you to understand that this whole complicated thing is just x squared. And then that's important because regardless of what we put in here, it will always have this behavior here. This behavior here. Okay? And what's important about it is what? If this is 0, where is it at? At the bottom, right? If it's 4, it's a little bit higher. Minus 4, a little bit higher. You see that? So 0 is where is at the bottom. That's just like almost like a coincidence, you can say, and this is why they use this function. Okay? Intuitively it works, but it's 0 at the bottom. When are these 0? When y equals y hat, which means when the real is equal to the predicted, which means you have a really good model, because if you have a model with really great weights that produces a value that when you compare it to the real gives you 0, then you're done. You stop training and you're done. But when you have a loss that's bigger, like 4 or minus 4, it doesn't live here, right? Where does it live? Up here or up here. Do you see that, guys? So the function governs that behavior, right? These variables, you plug them in, they result in something, but your goal is then what? To make the content here be 0, because if you do that, then you're at this blue little line down there, and you can't go any further. And you've basically achieved your objective because you only achieve that when you have like perfect prediction compared to the real. You see that intuitively? Okay. So that's a really important one. So my point is the loss functions create almost like this universe. And only in that universe do these functions live. They can never, like this function can never produce values like here or up here or to the right, only live in this line. Call it curvy quadratic universe. Those are aliens that only live in quadratic universe, okay? So you think of it that way. So here you live in maybe our real world, right? This is our real world, but this representation is quadratic world, another totally different place. All right, so that's governed because you decide, okay, the equation I'm going to use is the quadratic equation, which is MSE, y minus y hat squared. But there are other functions. You guys learned them, right? Sine, cosine, which is just like shifted a little bit. You guys learned those functions. You know they have a behavior like that. Polynomials, like something cube, right? It's got like a weird behavior, right? So you know of these, a circle. I mean, why not? Could be a circle, right? So different functions give different shapes. And in machine learning, we actually only use 3 loss functions. That's the amazing thing about all of it. You don't, it's not like maybe you were thinking, okay, I learned this, but now I have to learn a loss function for every single algorithm. Nope. You only have to learn 3. And 2 of them are the same for just binary and multi-class case. So really, there's really just 2 loss functions. And I already described one of them, the easy one, MSE. The other one is cross entropy. Yeah, go ahead.
Is there, I was actually gonna ask what is cross entropy?
Cross entropy is the second one, and we're going to cover that one in a lot of detail.
Okay.
So we're going to get to it for sure.
I noticed that in the code, I was like, I wonder if I can just swap this loss function out of something. It's like, why does this work?
Yeah, there's only 3 loss functions. MSE for linear regression and cross entropy that has the binary case and the multi-class case. And in general, if you see something else like something with a slight different name, it's probably a cross entropy that has some modification.
What would be the type where you just take the absolute value rather than the square, right?
That's absolute mean squared error instead of root mean squared error.
Okay. And sorry, and last question.
Yeah.
But what would be the one where you would just check if it's equal to the other? If not, if it is, it's output of 1, if it is.
That's the perceptron. You're thinking about, and that's a step function. But we'll talk about that one. Yeah. So right now, to me, this is really important because if you understand this, you're going to understand all the intuition behind this, as there's only one second case. That is the cross entropy, which has a crazy looking equation. And so that might throw you off. But if you understand this one, which has a simple equation, x squared, you can just like extrapolate to that one. Do you see what I'm saying? So really important. I recommend to you guys, do the exercise at home. Just draw a quadratic function like this one with some numbers. X squared, and then fill it in and just convince yourself that that's the truth, okay? All right, so to repeat, there are 2 equations, the inference equation, the loss equation. This is just for neural networks, by the way. I don't know other stuff. But in neural networks, we're just talking about 2 equations, inference and loss. Inference, you can see it right there. Y hat equal WX plus B, where these could be vectors. And that's where it brings in like multiple variables, multiple X's. So for instance, like an iris, we're talking about 4 X's, right? And 4 weights, okay? And then B is 3 because you have 3 outputs, okay? So that's the inference function. And then you decide that because you're doing regression, MSE is usually the good function for regression. Got it? Okay. Y equal y minus y hat, and this plugs in here, the blue kind of here. These 2 equations, and then each of these equations has its own representation. This is the inference, this is the cost function, and this quadratic is a fact that y minus y hat squared is really, it's shutting down. Y minus y hat is really, or y minus y hat squared is x squared.
They really need to fix.
Henry, I'm just a teacher here. All right, so, but let's give it a minute. I lost my pen today, so that's really making me sad. All right, so we'll start in a minute. All right, great. So two equations which look like this, and then this equation, the x squared, has this bowl shape, the quadratic, basically. Okay. So now what I want you to look at is the following. I took J is basically how you denote. You always use this convention of saying the loss function is J. Okay. So I'm taking y minus y hat squared, and I've rewritten it. And the only thing I changed is that where y hat used to be, now I plugged in what y hat is equal to, which is that wx plus b. But that's really important because since the points that whenever you select a point here, you're going to predict a point over here, right? You guys agree with that idea, right? So really, you give this value here and you get a value here. As it happens, what this graph captures is on the x-axis, you have values related to the function. Now, is y a function? No. What is y, in fact? Numbers, because it's the real values, right? So if you have the price of a house, y there is going to be $250,000, right? That's y. What is y hat? Y hat is a function, right? Given a value like square footage, which would be x, what is it going to predict? The price of the house. So if the real was 250,000 and it predicts 257,000, okay, it's getting there, right? It's predicting kind of okay. Do you guys see that? So those are the values that come in on this side, are the values related to this, but which values? Well, it's actually the w's here and the b's. Okay, those are the values that matter here. Let's just focus on the w, which you can see is what I've written down on the x-axis. W1, W2, and I guess W3. Maybe this one is W3. I don't know. But we have three variables there, okay? What is captured on this other side? Remember that what we were looking at is this idea that the blue line here is 0, but as we start moving out, it becomes 4 and so on, right? So intuitively, if it's 0 here, what does that mean? It means that the error was 0, because y minus y hat equals 0. So really, what you can say is that the y-axis here captures something about the loss, the thing that you're trying to optimize or minimize. And we usually denote it as cost. So it's like the cost. The cost is high. So with a bad set of weights, the cost is high. It is up here. With a really good set of weights, the cost is what? Low, right? Because it reaches the blue line. Can it ever be like this value here? Probably not, given this equation that I have here. But you're assured in a sense that this is pretty good, right? Certainly better than the values up here, right? Do you guys understand the intuition? So now you're capturing, by taking this difference, something about the cost. And you want to do what? Minimize this cost. And how do you minimize it? By reaching this point right here where the blue line is. So that is an optimization problem. So that takes us to optimization, and basically what we're doing in machine learning all the time. We're trying to play with these. Now, keep in mind, these values are going to change depending on these w's. Okay, so we have a bad w here. Imagine, just to keep it simple, that the w is +4. Something like that. And actually, this does not translate to 0, so I don't want to confuse you, but because it's the difference. But let's say that the w is just some value. Some value. Let's use another example. It's some value. Well, when you plug that value here, it goes into the function, produces a number. You compare it, you take the difference with the real number, square it, and it gives you this dot over here. So this dot basically means cost C2. So for W2, I was able to capture cost C2, and I fall right there. Does that make sense? Now I try another W, call it W1. So I plug that W1 in here, right? With the corresponding bias. I give it the X square footage. It predicts a housing price. I compare it with the real housing price, and W1 results in this blue dot here. Has that cost. A little higher than C2. So of these 2 points, which one is a better set of weights?
Probably close to 0.
The one closest to 0. So if we look at these two, you see this dot, right? Goes to C2, whereas this dot goes a little bit higher than C2. Does that make sense, guys? So that means that this weight W1 is worse than this weight W2. And you're assured by this relationship, this equation, that the best W is the one that gets to that point. Because what happens, let's say this is W3. So if the weight is W3, right? Plug it in here, right? Plot times square footage, predict housing price, compare it to the real housing price. That value is this one over here for W3. So what does that mean? At this point, you get C3. And what do you know about C3? It's better than C2 and this one. And so you have, in fact, done what? Minimize the cost. Does that make sense? So that's the set of, so the important thing to understand here is the W's, which are the value that the parameters that you're changing, govern this whole relationship here. And they're, in fact, the only value that you change, right? You don't change the X's. The X's are given. The Y's are given, right? The only thing you can learn is the W's and the B's. And if we look at this chart here, different W's will result in different C's, but the one that you want is the one that minimizes, because we've already established that the difference between these two, we want it to be 0, and that would be kind of at this point here. Does that make sense, guys? Any questions? It's a very important concept. So I'm hoping that you get this one, because to understand cross entropy, this is easier than the other one. Yeah?
So
Okay, perfect. All right. So one key thing, though, is that I have shown you different W's in this other equation, quadratic equation, give you different C's, right? But then the question is, how do you know how to optimize to get the best W's? Because still, I haven't given you a solution for that. So basically, all you know now is, okay, I need to change the W's. And eventually, if I get W3, that's the best one. So obviously, right now, maybe you can only randomly change the W's. You see that? But there's got to be a better way. And that's what something called stochastic gradient descent gives you. And that's where calculus comes in. That's the calculus part. But hopefully you understand that everybody always does this picture, but I want you to see that this picture is highly related to this equation. And this equation, you can literally code it in PyTorch, and it'll be the exact same thing, okay? So that takes us then to this part of the slide. If you notice over here, I have these two little boxes. This one over here and this one over here. So what you do is, in calculus, right, you can take a function and calculate what is called a derivative of it. At some point, if time permits, I'll just show you. Very basic, it's just a set of rules. Yeah, go ahead, Henry.
and the rate of change, so your change saying like W prime or something.
We have W, yeah.
What would you like? I know how to do this for the perceptron, but how would you do this for the stochastic gradient descent?
Yeah, so we'll do a simple example in NumPy where we implement this in code. But right now, just get the idea of what I'm going to try to give you, okay? So I think this is really important. So remember, guys, that I called this whole thing J, right? And I've already plugged in the W's in here, right? Because they're coming from the inference function. Do you agree? So I've made the whole thing into an equation. In calculus, if I have a function called x squared, the derivative of it, the first derivative is 2x. Just like that. Don't even ask me why. I'm not going to prove why that works. I just know that there's rules, right? X squared, the derivative is 2x. right? So that's basically a set of, you get a function, take the derivative, get an equivalent function. But it has meaning, though. That's really the important thing, that there's a meaning tied to that operation. And the meaning is something like this, okay? Which is what I'm trying to give you right now. So you are going to take the derivative of the function named j, which is basically this whole thing that I put in a square here, okay? You take this derivative and you're going to take it in terms of something, of one of the parameters. And so that's why this is written as the derivative of j in terms of the w's, or the derivative of j in terms of the biases. Do you guys see that? So we'll do this a little bit later on in NumPy and pure NumPy, but it's pretty important that you understand this, because what this gives you is it gives you information, which is really what you need. It's really awesome how this works. It's just like, imagine you have one weight in the neural network, right? Call it weight 17. How do you update this weight? The way that you update it is weight 17 equals weight 17 minus two things. One is the learning rate, which we've used already in PyTorch. It was that thing, it was 0.0001 or something. You can play with that parameter. And then there's the other thing that you multiply against. And that value is what you get from this. And all that you really care about is the sign. Is it positive or negative? You see that? So basically then when you're updating your weights, you have W17 equal W17 minus 1 times 0.001. Or W17 equals W17 minus plus 1 times 0.001.
And 001 is the learning rate.
The learning rate, yeah. Yeah, unfortunately, I can't write this stuff. But I think I have that equation somewhere in here, but I don't remember exactly where I have it. So I kind of have to describe it. But do you guys see that? So it might be in another PDF. Because unfortunately, I didn't write it down here. Do you guys?
The +1 and -1, the direction.
Yeah, the direction, yeah.
The that depends on, like, say, like, I don't know, like, oh, I have a class like this. I had it slightly more positive, supposed to be, you're just reinforcing positive, reinforcing negative.
I'm about to do this right now.
Oh, my bad.
I'm about to do this right now. All right, so you can see in this graph, we're not done with it. There's these blue lines actually have and imagine that before they weren't there, right? And now I'm adding this blue line here, this blue line here, and this blue line here. What are those? That's the information that you get from the derivative, okay? This is something you guys don't have to do. PyTorch does all of that with those three, remember, zero out grads, optimizer, backprop, and then optimizer step. Those three things are doing this. So PyTorch takes care of it, but it is important that you guys understand what's going on. So again, so what happens, right? Let's go back. We have J, we already established that. J captures the real and the predicted. The predicted is in terms of the W's, really important because it's the W's that we want to update. So we already established that a thing that is squared has this red shape like this. It's that quadratic function and nothing else. So now, just forget about what is over here and just think of J as a function. If J was equal to x squared, then the derivative of it is 2x. This J is not that, but instead it looks like this. But believe me, there is a derivative for this function, just like for x squared. Do you see that? There is one. Okay. And so you're going to take that step. You're going to basically do the derivative of J for this example, and now you get a new function. What's important about that new function is that when you give it values now, it's going to tell you the sign of where you're at in the function. What do I mean by that? So think of the red line, the red curve as this function, and think of these three blue lines as the derivative of j. Okay, so that's what you should think of now. Do you guys see that? Like these blue straight lines are now a superimposed new function, which is a representation of the derivative of j. What's important about it is you can do the following trick, and that just works because calculus. So you give it W2, right? That plugs into this new function. And now what it's going to tell you is that at this point, the shape looks like this blue line like that. Do you see that? That is called a tangent to the function, but really what it says is that function is slanted like this. And that's really important because it's telling you direction. If you're W1 and you're now in the derivative function, the derivative of j, this one, instead of, you're going to now be living in this blue line over here. Looks like that. And what this means is that this one is negative and this one is positive. And that's it. You don't even care about the value, but that symbol is really important. Why? Why is it really important? Because it's telling you which direction the downslope is going. It literally is like almost like a walking down a mountain. You're on a mountain and you want to know if you're, which direction should you go? Should you go in that direction or that direction? Do you see that? And that's what this blue line captures. So you can see, for instance, I did the derivative, plugged in the value W2, and I'm here. What do I know? I know this is the sign. So I know that it goes down in that direction. And it goes down in that direction towards the 0. Do you see that? If I'm on this other side, it gives me the plus, which means that the downslope is in the other end. How does that translate? Well, it translates because what you're going to do is you're going to say, let's say you're here, right? You agree that you're at W1, correct? If you're at this point, W1, okay. It tells you plus, yes? To get to the optimal, what should you do? W1 plus delta W, which is that little learning rate. So if you do W1 plus delta anything, which way do you go? Do you go in that direction or do you go in this direction? W1 plus little delta. Go in that direction, right? So you go towards the direction that is going to get you to the bottom of the bowl. Do you see that? Now, let's go to the other side. You're in W2, right? Remember, we already took the derivative of the function. We plug in W to that second function, and that function tells you minus. So it's indicating, but it's not that somebody calls you and says, okay, you need to take a step to the left, right? It doesn't work that way. But you do get that sign, and it's the equivalent of that. Because your W2, what do you need to do to get to the optimal here? You need to take W2 minus delta W. What happens if you do W2 minus delta W? You go in that direction. So eventually, by doing this over and over and over, you will get to the optimum. Do you guys see that? Does this make sense? And this is the algorithm, believe it or not, that trains anything from linear regression to ChatGPT. There's only one. Not 2, not 3, not 7. 1. And it's this one. And it took decades to perfect this stuff. Yeah, this is a key concept, okay, that you need to understand. So let's look at this example here. You're at this point, you're W3. This one does look like W3. All right, so you're at W3. Remember, the red is J, but somebody took the derivative of J, right? And that's the blue ones. So you have a second function, the derivative of J. You plug in W3 into that second function, and W3 gives you this here. What's the sign? Plus or minus?
It's 0.
0. It emits 0 at that point. So when you get 0, W17 equal W17 minus 0 times the learning rate. cuts out. So in theory, that should tell you in your mind, okay, I could get to 0 before I run out of epochs. That's a possibility, right? Or the other way is also possible, that you run out of epochs before you get to 0. Do you see what I'm saying? Do you guys see that? And how could that happen? If you start with bad values that are really high in this bowl and your learning rate is very tiny. Imagine that your learning rate is 0.00000001, okay? All right, just let me finish this one. So if you're W3 up here, W5, right? And you take the derivative, you do all the great stuff, you get the little line, it says it's minus, okay, what do? You take W5 minus, because this says it's minus, delta W. But that delta is so small that how big is your step? Your step is not that big. It's going to be this tiny step. And then you keep doing that and doing that and doing that. And if it's too tiny, you could do thousands of epochs and still be over here and run out of epochs before you actually reach this. So you're leaving money on the table, if you will, right? Yeah, Henry.
Would it be recommended practice to divide the epochs by your learning rate, so that way, no matter how your learning rate is, you're always going to.
The problem is you don't know.
I guess like you're saying, like, oh, there's especially small learning rate.
You got to do it experimentally, is what I'm saying. You don't always know. You have like a rule of thumb of where to start 0.03, for instance. But some learning rates, 0.1 might be enough, or 0.01, and others might need like 0.0005. But nobody really does that. I think I get what you're saying, like calculating how many epochs and figuring out.
Yeah, it's like, because you don't want the learning rate to get in the way of the epochs you want.
Yeah, but
so if you divide
if
you divide epochs by the learning rate, you're actually going to multiply the epochs.
I get what you're saying. My view of it is that you don't really like theoretically calculate it. You start with like a common, for instance, the Atom Optimizer has a default learning rate, which I think is 3 zeros and a 1, or 2 zeros and a 1, but it has a default learning rate. And then you give it a lot of epochs, as many as your machine supports and your GPU. And if you have a multiple GPU, even better. You see what I'm saying? Because you'd never know. Reinforcement learning, for instance, is one thing that could train for 1 million, nothing, and then all of a sudden, boom, it like shifts in another direction. So you got to experimentally figure this out. What I will say is that there's something called learning rate decay. And that's obviously more advanced, but you start with a learning rate that's big to take the big steps. And over time, what do? The learning rate becomes smaller for the tiny precision steps. Because another thing can happen, and this is what I was going to say. What if your learning rate is too big? Imagine you're a giant walking in this bowl. What's going to happen if you're a giant? You take a step here, the next step is going to be over here. And then the next step is going to be over here. So you basically like do ping pong from there, and you can never arrive to the bottom. You see that? So if the learning rate is too small, it takes too long. It's called to converge. And if it's too big, you may never converge, which means basically just you'd never get to the bowl, to the bottom of it. Do you guys understand though that the idea of walking is very real? You know, you're walking on this graph that exists because of this function over here, which is your choice, MSE. And the algorithm, literally, the calculus thing is just a second function that gives you this sign, plus or minus. That's it. Yeah.
And this scales into hyperplanes, right?
Yeah. This is you use something called the calculus chain rule, right? Because you have functions within functions within functions when you have neural networks. So you kind of have to like calculate all those derivatives. This is just for one. So, but we don't have to do this because PyTorch does it for us. We just give it the function and PyTorch will do it.
How, like, is it like, there's probably a good question.
Yeah, but
How does NumPy have the derivative of something if it's just like constants? Or my like.
no, you got to do it on a function. So I will do an example in PyTorch actually of calculating the gradients. What you don't have is it's kind of interesting is like in analytical calculus, you have x2 and you come up with 2x.
Right.
But in the way that it works here in PyTorch, you don't have that technically. You just have for every weight the resulting derivative of it. Like not the equation, but the value. That's what it is. So the values is what's stored. You see what I'm saying?
Right.
For that particular variable. But we'll see that actually. That's an example that I will do.
So it just takes like the next step. Someone finds the difference between the two.
It's in, so remember that when you create a model in PyTorch, you're creating a computational graph. Everything is linked, all the tensors, the data, the operations, and everything. And then you say, this is why we say requires grad. When we say requires grad, what are we saying? The W's require grad. So which means that when you take the derivative of the whole function, right, the weights are storing the value. Do you see that? So x2, right, becomes 2x. And if value is 3, then 3 times 2 is 6. So the 6 would be stored in. Do you see that? So that's the idea. But we'll do an example of that towards the end of the semester. But yeah, that's a good question actually, because for those of you coming from calculus, you're used to the analytical solution, which would be x2 and 2x, and then you're going to be worse 2x, and then you'll never see it. You only see the values. Make sense? Any other questions? All right, so we have like 9 minutes. So I think, let me just look at these slides to see if there's anything else. So I think I actually got through these. And this is like the intuition only of linear regression, only of MSE, and only for one weight. Okay, so this is only regression models are what the one where we predict temperature, right? Celsius to Fahrenheit. That's what I'm doing here. But what happens when you want to predict for MNIST or CIFAR 10, cat, dog, right? So you have 10 classes. So we got to look at that case, and that's different. That is done through another loss function, not this one, which is the one I said called cross entropy. But this whole process is the same. It's just, it's a different, definitely a different graph, sort of, not a bowl shape. The bowl shape is like the nicest, most intuitive thing to think about. Okay. All right. So let me look at these slides. So I think we finished this one. I did that. Okay. This one is, I think, the same idea. I guess this one, gradient descent is the algorithm. You can see it's the quadratic. It's just another example. Notice that I'm actually writing out here, W1 plus delta W or W2 minus delta W, given the sign that you obtain when taking the derivative. And this is basically taking the steps through the learning rate to reach the bottom, okay, where this one is 0, okay? I really wrote here, for instance, if you notice here, what does that represent? A very small learning rate. And these represent a really large learning rate. But that's what the learning rate is. If you've ever wondered, that's what it is, okay? All right. And then I said that, sorry, did you say something?
Yeah, is there like a way to like have like start out with learning rates of this of like a setting large amounts, and then like as you go on?
Yeah, I said that just now. It's an adjustable learning.
How would you do that?
It's very easy. Instead of saying LR equal 0.003, you say LR equal a function, like a K learning rate. You might have to tie it to the optimizer, I think, also, but basically that.
Right. Okay.
And that's it. It's actually straightforward. And it's standard procedure. You can try it. It would be a good idea. All right. So one last thing for this slide, because I don't want to. So this one, remember, it captures W to cost, right? So that was for MSE. MSE is a nice, linear, simple problem. People, mathematicians in particular, love linear problems. Neural networks are not linear. So the loss function of neural networks, for several reasons, does not look like this one. Intuitively, it looks more like this. Do you guys see the difference? This is a graph right here. Okay? So deep neural networks that are nonlinear, right? So let's say deep learning, an actual powerful 3, 5 hidden layer with activation functions, ReLU, etc., will unfortunately not have an MSE or bullshit. This will make mathematicians cry, right? Because it doesn't have that beauty of math. It has something they dislike, which is something that looks like this. They call it more like a black box approach. But it really looks like this. And this is what I want you to grab from this, is that it's more problematic. Why is it more problematic? Because in MSE, for the linear regression, you are guaranteed a minimum. You'll get to it. There's only one. But in this one, notice that it's got this bottom, and this bottom, which is probably, for this graph, the optimum. But you are not guaranteed in deep learning to reach that optimum. Why? Because you start with random values. So I always give this analogy. Imagine that this is a mountain range, these are valleys, and this is the base where you're trying to get, and then you throw in a whole bunch of paratroopers, like soldiers, right? So you randomly throw them on these mountain ranges. Some soldiers might fall here, some soldiers might fall there, or here, back here, or here. What are they going to do when your soldiers, let's say this is the clearest example. Let's say your paratroopers fell here. What are they going to do at that point? Take the derivative. Yeah. The derivative is going to say that they have a tangent like this, and it's going to say minus. So what are they going to do? They're going to take their W minus delta W, which is the learning rate, and which way are they going to go? That way. And that way, we'll keep taking them to this one. What's going to happen when they arrive here? They're at a 0 point. There's nowhere else to go. Do you see that? So the model will say that the weights, when they reach here, are the best. But that's actually not true, because there was this one, which those weights would have minimized the cost. Remember that on this axis, you're minimizing the cost. Do you guys see that? So this is why it's a good idea to randomize your initial values. It's almost like saying you throw some paratroopers here, and in another epoch, they fall over here. And hopefully in one of the epochs, they fell like around here. Because once you start to take those derivatives, it's going to start leading you into this valley. Long story short, once you're in one of these valleys, it's very difficult to get out. And because the function just is not built for that. But that's why you should do epochs, and you randomize every epoch. Sometimes you start here, sometimes you start there. Eventually, if you arrive here, that's the best set of weights that will be selected.
And if you had access to the distribution, you could just like set the rate to 0, find the critical point.
Where? Here?
Yeah.
No, yeah. So there's a lot of research in this, but this is very much like,
I think you had access to the distribution. Does that change anything?
I mean, if people study these functions, I can tell you that. Yeah, people study these functions for more optimal weights, but I will say, like, in all of the deep learning that we do currently, it's more of a, let's randomize it, let's give it a lot of epochs, and let's just hope that the model finds that valley and converges. A lot of people have
throwing things at the wall.
Yeah,
Okay.
exactly. This is how it works. Now, I read some study that said that basically it really doesn't matter, like that these do exist, but the differences are small, to the point where if you reach this one, your model is pretty good already. You see what I'm saying? So this is kind of where I believe this is at, right? Where they say there are differences, but there's so many of these differences that you're almost like probabilistically guaranteed to find a good one. How about that? You see that? But my point is, neural nets look like this. Okay, not like that one. So you're not guaranteed to get an optimal solution. Any questions? You guys get that? we'll come back to this idea. I actually have like a proof for this. So this one in particular, but we can come back to that. All right, these are, remember, we're just like digging deep into the concepts at this point. All right, so that's your stepper function that you were asking about, -1 + 1, by the way. All right, so this concludes these slides. It's 7:40. So we're done with this part. The next thing is probably logistic regression. So hopefully I'll have my pen by Thursday. Yeah, there we go. I feel like I'm missing something. And so we'll repeat this exact same discussion, but now for classification, for cross entropy. If you want, go ahead and read all the materials I provided. Once again, I'll point out, because this last part of the semester is more theoretical, right? Is more of the background of how neural nets work. I've already given you most of the code. We'll do a few examples here and there just to see how softmax works and cross XOR and things like that. But you really need to read all of this, okay? So it's in linear regression to logistic, all these links. Start reading. All right, guys, I'll see you Thursday.
This should be